Hi, ladies and gentlemen. Welcome to our next lesson. We're going to talk about Chapter 3 today. Just jump right into it here. And what we're going to talk about are the, going to get my highlighter set up here. We're going to talk about fundamental subspaces. But before we have the conversation about what the fundamental subspaces are, we need to figure out what vector spaces are and subspaces. This is the overview for Chapter 3. Just a few things that I want to highlight here. First of all, and he says, how do we define a vector space? And of course, that's a good question, and we'll talk a little bit about that. Obviously, we're not going to do any proofs associated with vector spaces, but it's important for us to understand the baseline ideas because they're so extremely powerful and applicable. Let's see. So, the key idea, and he makes this comment, the key idea is the connection to the simple laws of linear combinations. It's all about linear combinations. And we will see that the vector spaces are really defined by these linear combinations and making sure that they satisfy a preset group of properties. A little bit more commentary here. We're going to talk about the null space. We'll talk about that for a couple of lessons from now. And obviously what we'll do in the midst of that is we will do a go back on, and we'll talk about this today, the column space of A as well as the row space, which is the column space of A transpose. We think about taking that transpose and then the rows of A become the columns of A transpose. So the column space of A transpose is the same as the row space of A. And all of these subspaces are an important part of the conversation. One of the things we want to do is, and he makes this point, we're going to provide more information about what is a basis, what is the dimension of a vector space, and then what is the concept of span. And we'll talk about basis and span some today. One thing I want to highlight is the difference between where we've been and where we're going. And he makes this comment. He says in chapter 2, it was all about square matrices. We were talking about matrices that were n by n. And so when we were having the conversation about ax equals b and looking at solutions of that, whether or not we had one solution or no solutions or an infinite number of solutions, we were restricted to thinking about this in terms of square matrices. Now, in chapter 3, we're going to go to what he refers to as the higher level. We're going to go to general size matrices, m by n, where we have m rows and n columns, and there is no reason that the m and n have to be equal to one another. It is, the square matrices are very important, but the broadest application is for matrices that are also possibly rectangular. And we'll have that conversation. And where we're headed ultimately is to have the full conversation about the fundamental subspaces. And when we get towards the end of chapter 3, we'll be talking about those things. So let's take a look then. We have vector spaces and subspaces. And right off the bat, he talks about one of the most important properties, which is all linear combinations of vectors are going to have to be inside of our vector space, which really begs the question. Let's back out for a second. Let's talk about vector space. So a vector space really requires two things. It requires a set of things that we call vectors. Now, when we think of vectors that are in Rn. We think about the vectors that we've been talking about, but that is a very small viewpoint. The idea of vectors is considerably broader than that. And we can see in here, he has the conversation about vector spaces where the scalar multiplication is not necessarily done with real numbers, but rather done with complex numbers. There's nothing special about the real numbers other than it has a lot of applications. We could also be using complex numbers or something called a field. And we don't get into this. This is a higher level of conversation about linear algebra and vector spaces, but we can define this scalar multiplication using a wider variety of things than just real or complex numbers. We're going to limit ourselves to real numbers for this class. The other thing we have to be able to do is we have to be able to build linear combinations. And linear combinations require two things. We have to have a definition for adding these vectors together, and we have to have a definition for multiplying each vector by a scalar, which again for us is real numbers. So it's always good when we're introduced to something new to think about something that doesn't meet these requirements. We can think about lots of things that do, and we'll talk about those today, but what is a set of things that does not meet this requirement? Well, one of them is colors. We could consider a collection of 64 million different colors, but we have no way of defining addition of color. And what we certainly don't have any idea of is defining scalar multiplication of a color. What does it mean to take green and multiply it by 3? What does that give us? Now, what we could do is we could take those colors and quantify them into something like the RGB colors that we use, which are a vectorized set of colors. Even then, we have to make sure that we are what we say closed under scalar multiplication and vector addition. More on that later. But this is an idea of a collection of things that does not meet the definition for vector space. So we really need to get into the ideas of what a vector space is. And of course, he starts out right off the bat, the operation of linear combinations is fundamental. It is absolutely the fundamental piece of how we talk about and think about vector spaces. And then he talks about all linear combinations have to stay inside of the vector space. This idea is called closure. And we think about closure as we grab any two vectors from our set of vectors, and then we take linear combinations of those, and the linear combinations must stay inside of the set of vectors that we're talking about. Let me give you a quick example. Imagine we have vectors in R2. So if we grab any two vectors from R2, then those two vectors, when we take them in linear combination, we still get a vector that's in R2. That's guaranteed. So we are closed under scalar multiplication as well as vector addition because we're covered for all linear combinations. Example, again, a good way to think about things is think of an example where this is not true. Consider for a minute something you're familiar with, which is the third quadrant down here. So all the vectors that exist down here in the third quadrant, and of course this goes on to infinity in both directions, right? All of these vectors. Well, if I take any two vectors that exist down here, and let me do it in red, it might be a little easier to see. So that's a little hard to see. So I have two vectors that I'm taking from the third quadrant. Okay. Is the sum of those two vectors necessarily still in the third quadrant? If I add these two vectors together, do I have to stay in the third quadrant? Well, I'll let you think about that. It looks to me like that's probably the case. Anytime I grab vectors that have a positive x component and a negative y component and I add them together, I'm going to end up still with a positive x component and still with a negative y component. So it looks like I'm closed under vector addition. But what happens if I take one of these and I multiply it by a scalar, specifically a negative scalar? Let's say I take this first one and multiply by -1. Then I have this vector. That vector does not lie in the third quadrant. So the third quadrant is not closed under scalar multiplication. That means it can't be a vector space. In order to be a vector space, it has to be closed under all possible linear combinations. So all scalar multiplication, all vector addition. Continuing on with this idea, he talks about the idea of a subspace. So a subspace is still a vector space, but it's one that is a subset of a different vector space. An easy example for us, given R2, let's just stay with R2 for a second. What if I consider only vectors along the x-axis? Right, so if I take all the vectors along the x-axis, then what I have is I have vectors that are scalar multiples of 1, 0. And if I take any two of these vectors, so let me change from k to q times 1, 0. If I take these in linear combination, if I take any two of these vectors in linear combination, do I still stay along the x-axis? And the answer is yes. It is closed under scalar multiplication and vector addition. And as a result, it is a subspace of R2. It is a line in R2. And it turns out that any line that goes through the origin is a subspace in R2, or whatever dimension we're talking about when we're talking about real vectors. So a few examples. And you want to make sure and read through this. There's a lot of content in here where he provides examples and counterexamples to help you build your intuition as to what we're talking about. I'm going to do a little bit of emphasis on these two. The first one, he talks about matrix vector spaces. And this is something that can be a little bit confusing, so let me try to get it clear for you. So oftentimes we use capital M as the letter that represents a matrix vector space. Oftentimes what you'll see is script letters for vector spaces. So I'll try to use a script capital letter when I'm talking about a vector space such as M, or a vector space like V or W. I'll try to use that notation. So in this case, M is a vector space where he's defined the vectors to be 3 by 3 matrices. So each matrix is a 3 by 3 entity, like this. And it is a vector inside of the vector space M, which he is calling M is R 3 by 3. That's how he designates it. So it looks very much like R9, and he makes that comment. Right? He says, down here at the bottom, he says, in some ways, the space of 3 by 3 matrices is essentially the same thing as R9, but it's not exactly the same thing. It contains 9 pieces of information, but instead of containing those 9 pieces of information in a column vector, it contains them in a matrix. And our first question for the participation questions is why? Why would we want to do this? What are the potential advantages of representing things in a different way? When we think about these 3 by 3 matrices, again, we think about closure under scalar multiplication or vector addition. Let's say the scalars are still real numbers. If I grab one of these 3 by 3 matrices and multiply it by a scalar, do I still have a 3 by 3 matrix? And the answer is yes. So it's closed under scalar multiplication. If I grab two 3 by 3 matrices and sum them, I still have a 3 by 3 matrix. So it's closed under vector addition. The vectors themselves are the matrices, and they satisfy all the requirements for a vector space, which he outlines at the end of this section, right before we get to the problems. The next example, and the one that we're going to spend most of our time on, are function spaces. And this is the whole concept, and we're going to emphasize primarily polynomials. But this is not a big stretch to say, well, if I take, for example, the set of vectors 1t and t squared, and I think about all the linear combinations of these three functions, I could have a0 times 1, because that is one of my functions, one of my basis functions. We'll talk about that word in a little bit, plus a1 times t, plus a2 times t squared, and I think about all the possible linear combinations. What have I defined? I've defined all the quadratic polynomials. And the quadratic polynomials, again, it's a little bit of a thought exercise, but this is a vector space. If I grab any quadratic polynomial and multiply by a scalar, I still have a quadratic polynomial. If I grab any two quadratic polynomials and sum them, I still have a quadratic polynomial. From that standpoint, I am closed with quadratic polynomials under scalar multiplication and vector addition. And this concept, again, has to do with linear combinations and is at the foundation of defining vector spaces. All right, a little bit about subspaces. He goes through a lot of good examples here, and you want to make sure to take a read through this. The subspace concept really helps to solidify what the ideas associated with vector spaces are. But it's really pretty easy, right? We need a subset of vectors. And when I say that, of course, I mean vectors from a vector space. So that is going to mean that I've already defined what scalar multiplication is, and I've defined how I add vectors together. Those are two things that are up for definition, and those are already set by the kind of parent vector space. So I grab a subset of vectors, and then what I'm going to do is I'm going to check for closure. If I have vectors in the subspace and I have two scalars that are doing the multiplication, then I look for closure under vector addition and closure under scalar multiplication. As long as I satisfy those two properties, then my subset is automatically a subspace. And he goes on a little bit more, talks about some of the important facts. One of the most important, the only one I'm going to talk about. The rest of this, we're going to leave you to read through these examples. But every vector space must include the zero vector. And this means that the idea of a linear function, that when you think about a linear function, you think about a line. You think about y equals mx plus b. Well, it turns out that that's not a linear function by the definition of linear functions unless b is 0. Remember, I have to have, in my vector space, I have to go through the origin. I have to include the 0 vector, however that's defined. There's going to be more material for you to read, and the examples that he provides, that's all in here. He provides some more examples with respect to, and you want to take a look at these, examples 1, 2, and 3, having to do with the functions, having to do with the matrix vector spaces. Make sure that you take a look at all of those things so that it helps you have a good understanding of what's happening. Column space. So we've already talked about the column space, and we'll talk more about this next lesson. But it's important to realize that matrix multiplication is really a linear function. We can think of it in that way, and let me explain what I'm talking about. So on the matrix multiplication side, we say AX is equal to whatever it's equal to. I'm multiplying these two things together, I'll call it Y. So A times X is a vector. But let's back up for a minute. A, in this case, is no longer square. A is m by n. So it is actually taking a vector from some vector space and it's mapping it to a different vector space. And this is done by matrix multiplication. So we're taking the vector x and we're mapping it over to the vector y, which is really just A times x. Well, given any m by n matrix, doesn't matter whether it's tall and skinny or short fat, what vector size do I have to multiply by? This is m by n, m rows, n columns. I need to multiply by an n by 1 vector. So this side is Rn. I am taking vectors from Rn, multiplying them against A, and what I get out is a vector in Rm. And so we write this, and we'll see this next lesson. There is a linear function which operates exactly like a function based upon the matrix and matrix multiplication that yields a mapping from one vector to another. And it meets all the requirements of a function. So the reason this is important to us is for us to think about the idea of column space, because it's a little bit different when the matrix is no longer square. In the case where I have a tall, skinny matrix, and let me put some numbers to it. Let's say that my matrix is 5 by 2. Now what I have is, I have the column space is potentially a plane in R5. The output vectors, the input vectors, come from R2. The output vectors are R5 vectors. If my columns of A are linearly independent, then I have a plane in R5. That is the column space. So for this matrix A, the column space of A is a plane in R5. And again, that's with the assumption that the columns are linearly independent. I have two columns and they're not a repetition of one another. So the reason this is important is this now gets to subspace. So the column space of A is a subspace of R5. R5 is a vector space. Grab any two vectors in R5, take a linear combination, it's going to be an R5. What we have with the column space is we have a subspace, and this is the kind of importance of subspace. So let you look through this. We'll talk a little bit more about the word span, but make sure that you read through all of this material here. And we're going to talk about row space, and he really just outlines it right here. I talked about it at the beginning. The row space for A is the column space of A transpose. So let's expand on our example here. A transpose would be a 2 by 5 matrix. A 2 by 5 matrix is now mapping R5 to R2. If the columns of the original A were linearly independent, then I know that A has rank 2. And since the column rank and the row rank are the same, then I know I have 2 linearly independent rows. Well, but 2 linearly independent rows, when I take them in linear combination, gives me all of R2. So for A transpose, the column space of A transpose is all of R2, as long as my original columns were linearly independent. And that would give me, again, rank 2. So this idea of the subspaces for, you can think about it just like you do a function. I have a domain and a codomain. Originally, my domain was Rn and my codomain was Rm. When I take the transpose, it's flipped. I'm now mapping Rm over to Rn. That's for A transpose. We'll talk more about this next time. But it's important to understand that this whole conversation is fundamental to what we're going to talk about with respect to the subspaces of a matrix. One more point that we've already discussed before, the rank of A and the rank of A transpose are the same because the column rank and row rank for a matrix are the same. Finally, what we have is the word span. We've talked a little bit about span, but let me provide the definition here. The span is all, and that's the important part of this, possible linear combinations. And since it is all possible linear combinations, then it's going to be a vector space. The span of a set of vectors is going to be a vector space. And you could ask, well, how do I know it includes the zero vector? I know it includes the zero vector because one of the possible linear combinations is multiplying by the scalar 0. And if I multiply by 0 to every vector that's in my set that I'm taking the span of, then I end up with the zero vector. So it has to be in the span. The zero vector is in every span. A span, and we've talked about this some, let me give you an example. R3 is the span of what we know as the fundamental, or the standard basis vectors rather. Okay. That gets to our other word, which is basis. So a basis is just a set of vectors. A span is huge, right? It has all the vectors, all possible linear combinations. A basis is this small little thing. It's just a set of vectors. And when we think about basis, we're thinking about building blocks. We're thinking about, hey, what can we build with these vectors? And the really, besides this idea of building block, the only requirement for basis is linear independence, right? So a basis must be a set of linearly independent vectors. A set of independent vectors. That's the requirement for basis. If I have an independent set of vectors, then I have a basis, and when I take their span, I end up with a vector space. This gets down here to Strang's last question, which is, when do 10 vectors span R5? When do 10 vectors span R5? And kind of the flip side of that question is, when do 10 vectors not span R5? Could I come up with 10 vectors that do not span R5? Sure, that's easy. I could grab vectors of length 5 that look like 1, 1, 1, 1, 1, and then I could take 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, all the way down to 9, 9, 9, 9, 9, or 10, 10, 10, 10, 10, and I'd have 10 vectors that span a line in R5, one-dimensional, because the whole set is linearly dependent. Moreover, if I throw out any one of the vectors, it's still linearly dependent. How many vectors do I need to throw out before I get something that's linearly independent? I have to throw out 9 of 10. And with the one vector that's left over, I would have the same vector space when I take the span as I do with all of the vectors. These vectors are kind of redundant in nature. So the last thing I want to point you towards is this conversation here is done really well in Grant Sanderson's 3 Blue 1 Brown videos. So let me write this down. 3 Blue 1 Brown. You've already looked at these videos, but it's probably worth looking at them again. Obviously they're quick and they're very well done. Videos 3 and 5 are the ones where he talks about linear transformations. He talks about thinking of matrices and the matrix multiplication as linear transformations of vectors. Besides that, we have our participation questions. Throw those up. And the first one here has to do with, when would I want to use R2 by 2 versus R4 for my vector space? Right. So is there a reason that I might want to use one over the other? It's just something for you to think about. Another one has to do with a set of functions, and then finally down here it's about taking information about column spaces and building matrices from them. Thanks very much, and we'll see you in class.